We're going to work a problem with the coefficient of resistance built into it, but this is our kind of a fundamental differential equation which describes the spring with resistance. And my first problem I'm going to work is number 16 on page 355. So it starts off, a weight of 16 pounds stretches a helical spring 1 3/5 feet. Now helical means it's coiled like that, so it, it's just an ordinary spring. Okay. By the way, springs are more complicated than we're making these models out to be. I looked this up in Wikipedia, and boy, there's a lot of stuff on it, and a lot of other factors involved. So this is really kind of a basic model that we're working with. It's not truly as realistic as it could be. For example, a spring, once you stretch a little too far, then these some of these factors, some of these constants start to change due to the material it's made out of. So, there are a lot of issues going on here. So, but the basics here are studying a very good differential equation model, and it gives us pretty good information within a certain range of vibration or oscillation. Anyway, problem number 16, page 355. A weight of 16 pounds stretches a helical spring 1 3/5 feet. So 16 pounds stretches at 1 3/5 feet. Interesting number. I know why the author picked a number like that, because in the old days, 1963 is when this book was written, the pre-calculator days, textbooks tended to give you problems more often than not with some pretty friendly numbers, so you didn't have to do a lot of paper calculations. And I grew up in that era, and so when you took calculus, when I took it, angles tended to be 30 degrees, 45 degrees, or 60 degrees. Okay, because we knew those exact values for trigonometry. Well, anyway, let's get on with it here. The weight, see what we can figure out. The weight is mass times gravity, but according to Hooke's law, it's also proportional to the length the spring is stretched. And so a weight of 16 pounds is K times 8/5 feet. And so we work out K would be, I believe, 10. So the spring constant for this problem is 10. And all right, now then, I guess that's good to know. Now also up here, omega squared, another useful formula, replaces G over L. And so if I plug that in, omega squared is 32 feet per second squared divided by 8/5 or 1 3/5 feet. And we get, this is feet per second squared. Okay. My units are just going to give me, because the feet cancels, my units are going to be 1 over second squared. And when we solve for omega, it's going to be 1 over second, or hertz. So let's not worry about that so much right now. All right. So what's 32 divided by 8/5? I think it's going to be 20. 20. Yeah. Just invert, multiply, divide. Omega squared is 20, which makes omega equals to the square root of 20, or if you like to, we can simplify this down to 2 square roots of 5. All right, so what is the square root of 20 is about 4 point something, isn't it? I just realized I left my calculator in the other room, so I'm going to interrupt a moment. I found my calculator, and omega is about 4.47 hertz. All right, so with disregarding the resistance in the spring, the natural frequency of the spring would be about 4.5 times per second. So it would bounce up and down 4.5 times per second. That's that's quite a bounce, isn't it? That's pretty fast. All right. Well, we'll see what happens when we put in the coefficient of resistance, how that changes this problem. Now the next part is a coefficient of resistance of the spring is 2, equal to 2. Okay, so let's see, the coefficient of resistance is 2 times mass times R, and it's given as 2, which means mR is equal to 1. But we have to figure out the mass, and a 16-pound mass is mass times acceleration. So its mass is slug times acceleration g, 32 feet per second squared. And so weight, mass times acceleration, that means that the slug is going to be 1/2 slugs. So is the mass of this weight. So plug 1/2 into here, 1/2 R equals to 1, that means R equals to 2. So it was coincidence that the coefficient of resistance was 2 and that R was also 2, and that's because of the 16-pound weight having being 1/2 of a slug. Alright, well, so let's plug our numbers in up here and we'll work this out. R was equal to 2, so this gives us 4 y prime, y double prime plus 4 y prime, and omega squared was 20, plus 20y equals to 0. So, there we go. Let's solve this equation. The characteristic equation is m squared plus 4m plus 20 equals to 0. By the way, I didn't tell you the rest of the problem. The rest is that it, after it's brought to rest, is given a velocity of 12 feet per second. So at rest, it's given a velocity of 12 feet per second. Alright. So that kind of completes the statement of the problem. At rest means that the initial position is 0. It's not, hasn't been pulled down and let go. It's right there. However, at 0 it's given an initial velocity of 12 feet per second. That would be downward, so it's like you tapped it and it started off at 12 feet per second. So these are the initial conditions. Okay, back to this problem. We solved this characteristic equation. M is equal to, I'm going to use the quadratic formula. You know, A is 1, B is 4, C is 20. So M is minus B, plus or minus the square root of B squared, minus 4 times A times C, divided by 2A. And let's see here. This is going to be negative 4 plus or minus. Here I've got 16 minus 80, which is minus 64, square root of minus 64, divided by 2. So that would be minus 4 plus or minus 8i. Square root of 64 is 8. The negative makes it 8i, an imaginary number, all divided by 2. And this comes out to be minus 2 plus or minus 4i. Alright, so let me write that up here. The root of the characteristic equation is negative 2 plus or minus 4i. Alright, well that's going to allow us to write out a solution. In writing out a solution, we have to decide if we're going to use sine or cosine. Which one do we use? Well, this problem begins at the origin, or begins at 0. And the sine function, sines, without any phase shift, the sine function starts at the origin. So sine is the best choice here. Now, if it had started somewhere else, then we probably would want to use a cosine function, because cosine starts above the axis. So let's use a sine function. I think it'll render our phase shift delta equal to 0. So we have c sine. Actually, how does that work? It's c e to the minus 2t, because of the negative 2 here. And then sine of 4t. There we go. Oops, parentheses plus delta. All right, so the real part of this number, of this root of the characteristic equation, -2, appears as a coefficient of time over here as an exponent of e. So e to the -2t, and then sine parentheses 4t plus delta. The 4 is the coefficient of time there. There we go. So we need to solve for our two constants, c and delta. And I suspect c is going to be equal to 12, because that's the... No, maybe it's not. I don't know what it is. Because that's that 12 up there is a velocity. We're not sure how far it's going to stretch. So we'll figure it out. Let's go ahead and take the derivative before we plug numbers in. So the derivative is going to be, this derivative is minus 2c e to the -2t sine parentheses 4t plus delta. And then, product rule, add plus c e to the -2t times the derivative of the sine. So it's going to be plus, and this derivative is going to be cosine times 4 because of the chain rule. So I have 4c e to the -2t, and then cosine 4t plus delta. There we go. Alrighty, now then, y at 0. Well, I plug 0 in. Up here, I get c times e to the 0, that's 1, c times 1, times cosine of, times sine of delta, and that's equal to 0. So, kind of been through this before. C has to be non-zero, but delta is going to have to be 0. So, our phase shift is 0. Just what we wanted, because we chose a sine function. Our phase shift is 0. Had we made this a cosine, it would have been more complicated. Maybe the phase shift might have been pi over 2. Okay, so we know what delta is. And to get the other one, we're going to have to plug in to the first derivative. Y prime at 0. Alright, so I go over here, plug zeros in, and e to the -2t is 1. So I have minus 2c times e to the 0 sine, that's 0, sine of 0, plus 4c e to the 0 cosine of 0. Great, well, sine of 0 is 0, and cosine of 0 is 1, e to the 0 is 1, so I have 4c equals to 12, which makes c equals to 3. There we go. So I'll do some erasing. We'll write up the equation of motion for this problem, and then we'll see what other questions we can answer with it. Our equation of motion then is y of t is 3e to the -2t sine of 4t. And I double checked it, it's correct, no screw ups. Now so the book in part A asks for that equation of motion. It also says draw a rough graph of the motion. And so let me see here. I'll draw you a rough graph. Now the maximum it could ever hit is 3. And actually it doesn't hit that high because the oscillation starts right here at the origin. So here's t, time. And we send it into motion, and it kind of peters out over here. So it goes up, comes down. It's not going to hit quite 3 because of the damping factor here, e to the -2t. This is what's shrinking this oscillation, the sine wave down as we go to the right. And is this factor right here. So it doesn't quite hit an amplitude of 3. I'm not sure quite how high it gets, but that could be figured out if we really wanted to know. This is the y-axis. So kind of a rough graph, And let me do this. So there's this curve which is y equals e to the, actually 3e to the negative 2t. 3e to the negative 2t, and if I reflect it, it's down here. And that's called the damping factor, I believe. Yeah, the damping factor. This is one of the questions in part B. The damping factor is 3e to the negative 2t. Alright, so you want to think about the damping factor as sort of a boundary in which this oscillates, the sine wave occurs. And so it compresses the sine wave according to the boundary of that curve. That's called the damping factor. So, and it's just literally the coefficient of the sine function in this case. Now they also want to know the damped amplitude. The damped amplitude, or the the damped amplitude is oh, wait a minute, I'm a little confused. So let me resolve my confusion here. The oops. Well, the damped amplitude is 3e to the negative 2t. Sorry about that. The damping factor is just merely e to the negative 2t. So I've got that a little backwards here in my mind. So the damping factor is e to the negative 2t, but the damped amplitude is the product, 3 times e to the minus 2t. And it is the damped amplitude function which provides the boundary, not the damping factor, as I said a minute ago. Alright, so kind of get that terminology straight. I don't normally think in terms of all this terminology that the book does, and you'll see why in a moment. The next question is the period, or the damped period. So I'm going to erase this graph. I tend to just call it the period. Our book calls it the damped period. And the period is how long it takes for one cycle, or one complete down, up, and back motion. So we hit this thing, it goes down at 12 feet per second, so it drops down, bounces up, and comes back to equilibrium. How long does that take for one of those cycles? That's called period. So the period is measured by 2 pi divided by the coefficient of the time. 2 pi divided by 4 is pi over 2 seconds. So, which is about 1.57 seconds. So that's how long it takes for one complete up and down. About 1.57 seconds. And incidentally, it will continue to take that amount of time for each cycle. So even though the amplitudes are shrinking, and eventually comes to rest, the time it takes for each cycle remains constant. And you can observe that with springs, and a good thing. If it didn't work that way, the a two-dimensional problem like this would be called the string vibrating string problem. For example, if you have a vibrating string, it bears some resemblance to this problem, except it takes place in one extra dimension. And so if you pluck a string on a guitar or a violin, if the frequency changed with each vibration, then we would not have music as we know it. And but since those frequencies remain the same, then the sounds don't change pitch as time changes. All right. Well, that's the period. Now the frequency, or book calls it damped frequency, is literally just the reciprocal of the period. So it'd be 2 over pi per second, 1 over seconds, and that's hertz. And this is approximately, what is that? Around 0.6 something, I think. 2 divided by pi is about 0.64, 0.64 hertz. So in terms of frequency, that means that it does 0.64 vibrations in 1 second. Okay, not a full oscillation or vibration, but only a little over half of a vibration. Now, I looked this up in the book, and I've looked this up before. This book tells us, gives us a different number. The book says it's 4 radians per second. 4 radians per second is the frequency. You know, radian is an angle measure, and I think I'd be a lot more interested in a time measure than an angle measure, but it's what the author uses. And anyway, the damped frequency is literally the that number there, 4 radians per second. That's where it comes from. So it's kind of easy to get. You just siphon it off to here. You don't have to think about converting this to radians per second. I don't think it's terribly important myself. And maybe there are some engineering applications where that's more interesting than hertz or time. But anyway, I don't like to do this. I'd like to do it in hertz. All right, next thing is called the time constant. Now I had to look this up, and the time constant is 1/2, I believe. And it's another one of those things that if you had me for a class, I'm not going to ask you the time constant, but the time constant is 1/2 second. Time constant. And maybe this has some real value. The book explains where it is, and page 351, it says the time it takes the damping factor to reach the value of 1/e is called the time constant. And it's literally 1 divided by r. 1 divided by r. And r was equal to 2, wasn't it? It's 1/r. And so it makes some sense, I guess. I think more of a graphing sense than an interpretation sense. So, I don't know. It's probably useful to some people. I don't tend to look for those numbers. Okay, the ones I'm most interested in here, I like this, and I really want to know what the frequency is. Okay, so, and by the way, the coefficient of resistance did slow that spring down, didn't it? Remember, we had it bouncing pretty fast before we put this factor in. When we put that spring constant, I'm sorry, the coefficient of resistance in, it slowed the spring down considerably, and to something more realistic. So, I imagine kind of a loose spring, man. This thing's just to bob it up and down like this. And it's a rather large spring. Okay, well, the other questions, I don't know. Let's see if they're worth looking at. When will the weight stop for the first time and change direction? How far from equilibrium will it be then? Well, let's see if we can get that. So, back to the graph. Let me get that graph up here again. Here's a rough sketch of our equation of motion again. And the question in part C is, when will the weight stop for the first time and change direction? And how far from equilibrium will it be then? So they want to know, when does this peak out and how long does it take? What's the time and how far does it take? How far does it go, rather? Okay, so in other words, we're looking for the maximum of this function. Now, if we look at the derivative, we can get that, I believe, relatively easy. So back to the derivative here, y prime of t is going to be minus 6 e to the negative 2t sine 4t, and then plus 12 e to the minus 2t cosine 4t. And we want that equal to 0. Gadzooks. Because that's what happens up here. The velocity comes to halt at 0. And so the first derivative is velocity. You have to set the first derivative equal to 0, and it that derivative involved the product rule. So I better make some room for this. I'm going to factor out 6 and e to the minus 2t. 6e to the negative 2t. And that leaves 2 cosine 4t minus sine 4t equals to 0. All right. So, oh boy, well, this part can't be equal to 0. That means 2 sine 4t minus sine 4t must equal to 0 to solve that. So 2 cosine 4t would have to equal to sine 4t. So I took, this factor is non-zero. To solve this problem, I set this factor equal to 0, which brings sine over to the other side. And if I divide by cosine 4t, I've got 2 equals to the tangent of 4t, because sine divided by cosine is tangent. So 4t will equal to the inverse tangent of 2, which makes time equal to 1/4 inverse tangent of 2. Oh, wow, okay. So, if I work that, well, we gotta be careful. Because the inverse tangent gives us an angle, doesn't it? And in calculus, because the way all the derivatives are calculated, we have to work in radians. If you try to work in degrees, you're just going to get nonsense. So all the derivative formulas in calculus based upon radians, all the ones involving trigonometry. So I've got to make sure my calculator is in radian mode, and it wasn't. Okay, now it is. So let's see. The inverse tangent of 2 is about 1.1 something times 1/4. This is about 0.28 seconds. Now I kept all the decimals in my calculator, but I'm not interested in reading all those decimals, but I do want to calculate with them. So about 0.28 seconds, it started off at 12 feet per second. It goes down, and just before it starts to come back, that took just under 3/10 of a second. All right, and then how far did it go? So now I'm going to take this number and plug it into this equation here, and so this function here. So I'm going to store all my decimals into my calculator, into the memory. I did store x basically. So 3e to the parentheses negative 2, I'm using x, not t, negative 2x, times sine parentheses 4x, close parentheses, is 1.54. So 1.54 feet. Alright, now if you're my student, I'd like to ask for sentence answers. So the spring, I wrote out the answer. I like to require that out of my students. The spring first comes to rest after 0.28 seconds and is 1.54 feet from equilibrium. So, and I looked it up, that's correct. So that worked out good. Alright, well, the rest of the problem, part D asks, when will it stop for the second time? Well, we would have to do what? Well, we'd have to add our period to time. In other words, the period was what, 1.5 seconds or pi over 2? We'd have to add that to this number and then plug it in, and then we can see how far it went. Well, let's do that real quick. I'll just do that on my calculator. So I had stored as x this time value, and one period takes pi over 2 seconds, 1.5 seconds. So to this decimal number, I'm going to add pi divided by 2. I get 1.847 something seconds. And so I'm going to store that as x. Then I'm going to go back and plug it in to our function here, and now it is 0.67 feet from the origin. Let's see, did I get that right? Boy, I sure hope so. Yeah, it didn't really. No, they've got. Oh. Huh. I screwed up. All right. Misconception here. Let's get this right. Okay, this was after 0.28 seconds, right? And when I added pi over 2, my period, that brought me to this point. And that's wrong, because if I want to know when it stops the second time, I have to take half of the period, which is not pi over 2, but pi over 4. So if I take my original value of x and add pi over 4, then I get 1.06 seconds. And now, if I plug that into my original function, I get minus 0.32 feet. Alright, let's see if that's what the book got. The second stop, the book said it was minus 0.32 feet. Good. Alright, and they added pi over 4 seconds, just like I did. Alright. And then part E, write a formula which will give the times when the weight crosses equilibrium position and for the times of its successive stops. Don't mess with that. It's just, I don't know. It's if you have this book, you can look up what they got. They had a periodic function they came up with. All right, so this is kind of a basic problem involving the coefficient of resistance, and let's do another one.